The European alchemists of the 12th century sought to find the philosopher's stone, a substance that would transmute base metals, such as lead, into precious metals, such as silver and gold. Today, we will be discussing whether data analysis, including machine learning, can transmute base laboratory data into precious clinical tools. We'll use antimicrobial susceptibility testing as a case study for new applications of data analysis. Some of the questions we will address include: how can relatively simple datasets be used to build upon current methods of verification of antimicrobial susceptibility testing? How do commercial systems analyze individual susceptibility results, and can we improve on this analysis using new methods? And finally, what is the long-term potential for leveraging laboratory data and other clinical data to improve and support clinical decision-making? And what needs to happen to realize this goal? Welcome to Editors in Conversation. Please subscribe to the podcast and rate or review it. This episode is brought to you by the Journal of Clinical Microbiology, available at jcm.asm.org. I'm Alex McAdam, the Editor-in-Chief of JCM. Editors in Conversation is supported by the American Society for Microbiology, which publishes JCM. And if you are a member of ASM, you can get up to 50% off publication fees when you publish in JCM or any of the ASM journals. I am joined by my co-host, Dr. Ellie Thiel. Ellie is, of course, an editor of JCM and a clinical microbiologist at the Mayo Clinic. Welcome, Ellie. How are you?
I'm pretty good. I have to, for those of us or those of you watching the video version, you'll notice that Alex, your office looks different. Where did you go? Did you change offices?
I am in the same old office, but it's a double-sized office that I wasn't sure whether I was going to be able to keep long-term. And now I have found out that I am keeping it long-term. And so I had a bunch of stuff ripped out from back there, and the wall is hideous. So I have just rotated my monitor and camera, and I took all the junk that was behind me on the desk here and moved it over there and put the Manual of Clinical Microbiology on the table as a prop. How do you like it? Rate my room.
10 out of 10. I think it's very clean.
10 out of 10?
I cleaned my desk area here.
What's that little stack of papers that's peeking in?
It's usually all this stuff from a review I recently, or still am trying to write, actually. And I can't read papers on the computer. I got to print them.
Is it your CMR review?
It is. It's the CMR review. Good. That's like never going to be written.
When did you agree to write that review?
Okay, March of 2020. But then the pandemic hit.
You were busy.
So I feel like that gives me 2.5 years. Yeah. Right? So really, I'm only 2 years late. Right?
I guess. Do you want me to rate your room?
Rate my room.
I'll give it a 10. I like the mosquito, especially. Yes, I've always liked the mosquito.
There's also a disco ball.
No.
You see the disco ball?
Oh my gosh.
There it is.
And if you're listening, go to your computer. You need to see the disco ball. And I was off. Why is there a disco ball?
Well, because that's the type of music I like. I like vector-borne diseases and electronic European dance music.
So if your office reflects your likes, then I guess I like large empty spaces that are in need of decoration. All right, let's get into it. Our guest today is my friend from right across the bridge over at the Brigham Women's Hospital, Dr. Sanjot Kanjalal. Sanjot is assistant professor in the Department of Population Medicine at the Harvard Pilgrim Health Care Institute and an associate medical director of clinical microbiology at the Brigham and Women's Hospital, as I said. Sanjot, welcome. Thanks for joining us.
Thanks for having me.
You have a really interesting mini review in press at JCM. It's not in press, it's in the current issue. And the title is The Modern Alchemy of Clinical Pathology, Turning the Output of the Microbiology Laboratory Operations into Gold. I think the title and my slightly florid introduction have set the stage, so let's go ahead and get into it. Much of your work focuses on the use of machine learning to improve and support decisions in clinical care, using the data generated by the clinical microbiology laboratory. Before we get into the microbiology, can you define for us what machine learning is and how it relates to artificial intelligence?
Sure thing. Thanks a lot again for that introduction and the florid introduction, as it were. Never been quite introduced like that before. But to your question, it's interesting. Machine learning and AI or artificial intelligence have tons and tons of definitions out there. But I think it's sort of generally agreed that machine learning, or ML as I'll refer to it, is a subfield of AI that's focused specifically on the development of computer algorithms that help software programs learn through experience or learn through data. And that data is usually referred to as training data. And then you see how well the model learned on a different data set that it hasn't seen called test data. AI is really a field that is broadly dedicated to the design of intelligent agents, which are defined as things that act with purpose, are flexible to their changing environment, learn from experience, they make rational decisions. And it's really interesting because, by that definition, artificial intelligence can involve living and unliving entities like a computer.
Mm.
It can involve individuals, it can involve societies. It's a very, very broad definition, and ML is just one piece of that. And just because I think a lot of people are also ask me, what's the difference between machine learning and statistics? I would say they're both very closely related and they complement each other, but they are fundamentally focused on different problems and using different approaches. And machine learning, I think, is really focused on building algorithms that then use statistical models on pieces and of subsets of data to generate a more robust statistical inference.
So to take an example that people would be familiar with, ChatGPT is a large language model. That is an example of machine learning, yes?
That is correct. Yes.
Gotcha.
ChatGPT is built over something called a transformer architecture, which itself is just a newer version of a deep neural network.
Great. Well, thank you for that. I think, we're hearing more and more about AI and machine learning and using that in microbiology. And I think every time I hear about it, I need a refresher on the definitions. so that was helpful. So kind of zeroing in on Clin Micro then, really, what kind of areas, I guess, in micro would be adaptable for machine learning, and what are some of the challenges of accessing and using the data that we put out from the laboratories?
That's a great question. I would say so. Thinking more broadly, machine learning is simply a tool. You start with the question or the problem and see whether the tool applies to that problem. One of the biggest mistakes I see is someone develops a tool and then tries to find a problem to solve. That never works well. But in terms of what are the problems in clinical micro to which ML applications can provide an advantage over existing approaches, there's a lot. And a lot of it has to do with the types of data that go into the model, garbage in, garbage out, but also treasure in, treasure out. And I think the one of the advantages of ML is its flexibility to the many different types of data that gets fed into a model. It's somewhat agnostic to it, and unlike sort of traditional defined statistical models where you make assumptions about the distributions of the features that go into it, you have a lot more flexibility with machine learning algorithms to not have to make those rigid assumptions about that. And by doing so, you can actually generate some, I would say, fairly robust insights, but require a lot of validation and sort of critical thinking about the results. In terms of sort of what data can go into it, almost anything can, but I would say the sort of most accessible will be data types that are the ones that flow from the lab that eventually come into the EHR anyways. And so examples can include, the metadata associated with the specimen, such as the location, specimen type, timestamp, obviously the organism name, susceptibility profile, which can be quantitative or semi-quantitative in nature. For molecular assays, it can involve CT values, viral loads, genetic targets. And these data are not the most accessible to pull, but depending on your healthcare system, they usually reside somewhere in a clinical data warehouse. And so to use it, you have to write queries to this data warehouse, usually a data SQL database, have space somewhere to store the data that you pull from these databases, and then have the ability to write analysis scripts that look at the data stored on these clusters and actually clean it and visualize the results. So I'll just give you one example from our system. I have a set of scripts which I pull from a shadow of SunQuest and a shadow of Epic, meaning that I'm not pulling directly from Epic because if I mess something up, that would be terrible.
Yeah.
Mm-hmm.
So we have a mirror, and I pull from that mirror, and that mirror is delayed from the real time by a day. And so that prevents any sort of errors from entering the medical record. I then store that data in a shared file space and perform analytics on it using Python, which we have a Jupyter notebooks to do that, and R using something called RStudio. Now, Jupyter notebooks and RStudio are installed on what's called a Linux high performance research computing cluster. And so I've taken the data from the clinical data warehouse, moved it to the computing cluster, and then that cluster has the software for me to interact with the data and visualize it. When I form a plot or a graph, I then export it out of the research computing cluster and send it to my colleagues for analysis.
Mm.
For computationally heavy operations like calculating parameter weights for a deep neural network, I direct jobs to nodes on that cluster that contain what are called graphical processing units or GPUs. But for the vast majority of operations, including everything that I describe in the article, a simple CPU is sufficient. I would say that it takes a bit of learning to learn how to build these pipelines. I'm self-taught, so if I can learn it, I think anybody can learn it. But once the operation is running, it's quite powerful. I would say I can now, like, I get people asking me, "Hey, what's the resistance of Elizabeth Kingella on to this antimicrobial?" And I'll usually say we don't have enough data. But if there is enough data, it's so easy to just query the name and the antibiotic, and it gives me an MIC distribution. And I can do it over time. I can do it per hospital, per unit. It's extremely flexible. And the added benefit is I've also set up the pipelines to pull the metadata associated with the patients who have this particular organism. So I can pull their comorbidities, prior antibiotic exposures, and things like that, and turn it around in about a day. So it's took. I'm not going to lie, it took me several years to build this, but now that it's built, it can be quite powerful for what I'm trying to do. I'm the we'll talk about the future later, but I'm very excited about certain developments that are happening right now, which will allow me to actually pull data directly off an instrument, such as a growth curve on a blood culture incubator, or a Vitek, or a mass spec profile, or a amplification curve on a PCR, rather than actually looking at the CT value or the time to positivity. And I think that's where a lot of my interest lies in the microlab.
Got it.
Very cool.
You make it sound so easy. I mean, I'm almost
Didn't
ready
sound
to go
easy to me.
do it right now. Well, it just flowed so straightforward. Aside from all the acronyms you threw at me,
I'm pretty sure if I can learn it, you guys can learn it.
Well, that's encouraging. So, kind of getting into your article, you went through several examples of potential uses of data from the microlab. And the examples that you really used for your study focused on antimicrobial susceptibility testing. So, can you talk about why you used AST data, for example, instead of serologic or molecular testing information and data?
Yeah, of course. I would argue that there's nothing particularly special about antibiotic susceptibility testing or AST data that makes it more or less suitable for data analysis. It's just as messy as anything else out there. But I simply chose it because it's the type of data that I know the best from my own research. And so I could speak a little deeper about AST data. But I've worked extensively with respiratory virus data using the exact same algorithms. And that's what I think is one of the nice aspects about these types of analyses or pipelines is once extraction and analytic pipelines are built for a set of common analytic tasks, look at a distribution, compare this cohort to this cohort, it's actually relatively straightforward to expand those to cover more data types or analytic questions as they emerge in the lab. And I want to be clear, like many, if not most of the methods I mentioned in the article are simply ones that are the lowest hanging fruit in terms of immediate practical impact. And those are just simple descriptive statistics that don't rely on anything other than a t-test or a chi-squared test. And the magic really lies in building the infrastructure to extract and clean that data in an automated fashion with validation checks to ensure it's accurate. And so once that's in place, the applications start expanding downstream.
The first application that you talk about in the paper is data-driven verification or re-verification of susceptibility testing panels. And I think our listeners will mostly be familiar with conventional phenotypic verification of AST panels, where the new panel is compared using isolates that have known susceptibility results to some reliable testing method. So what are the challenges or the shortcomings of that conventional phenotypic verification?
Yeah, I mean, I just want to say manual phenotypic verification will always have its place in the lab, particularly the first time a card is being introduced into use. I mean, to me, there's still nothing as good as hand generated data by experienced people. The issue is that that requires time and effort by people, and time is a hot commodity, and staffing is a hot commodity. And B, there is sort of, at least for a manual verification, implicit assumption that the behavior of the small sample set that you use, the behavior of those organisms, reflects the behavior of the organisms in the pathogens encountered by patients in your health system. In most cases, it's probably a totally safe assumption. However, we do know from decades of bench work and experience that bugs can have a wide range of behaviors when taken out of hosts and grown in nutrient rich medium. Couple that with the fact that the population epidemiology of pathogens in a given area is under constant selective pressure and is continually evolving, you can envision a situation where the initial performance of the carb may drift over time in ways that are perhaps not predictable or at least difficult to predict. And that may not be captured by use of QC organisms every 2 weeks or every week. And so that daily variability, of course, is why we have so many checks in our workflows for when atypical results appear. And that makes total sense for patient care. But taking that information and utilizing it to re-verify the performance of a card is actually pretty hard. And so that's where I'm arguing that we need to build these sort of external to our current workflows to then allow us to do this on a continual basis.
Good. So let's talk about those. Walk us through how a data-driven method could add to the conventional verification testing.
I would say the base concept of a data-driven method for verification is the idea that we can generate an expectation for how panels should behave towards a given bug-drug combination through our own repeated routine use of the panel. And eventually, we can generate a distribution that is fine-tuned to local pathogen epidemiology and local host characteristics. And then these distributions can be simple SIR phenotypes, but I actually think actual MICs or KB diameters are more informative. And what is cool is that as more data accrues, you develop sufficient sample sizes to start performing stratified analyses by common clinical characteristics like location or body site. And I describe an example of this in the paper. I start by showing, in figure one, I start by showing the overall distribution of MICs to piperacillin, tazobactam, and Klebsiella pneumoniae. And that's sort of our starting point in the upper left-hand side of the figure. And then the first thing I do is I stratify in two ways. The first is, say, we want to look at by hospital location, and then the second is by body site. You can then further stratify by inpatient, hospital location, or blood as your body site. So the key insight here for sort of analysis of if the performance is changing over time is to then establish a time interval and then stratify the distribution at that body site or location by that time interval. And in the figure, I chose a 1-year time interval from 2019, 2020, and 2021. And then I did a simple statistical chi-squared test to say, is the distribution from 2019 different than 2020 and 2021? And then in the table below that, I show that, yes, in fact, it is different between 2019 and 2020 and 20 versus 21. At that point, it's up to the lab directors to interpret whether this constitutes sufficient evidence to trigger reevaluation of CAR performance. And if they think that the answer is yes, one should redo the verification by hand with local strains rather than external strains. And that way you're having a better insight into sort of how it's performing now with the epidemiology of your current healthcare system. And if the card doesn't pass verification, then you need to do more work at that point to understand why. But regardless of the outcome, the whole process is iterative. And so even after you finish the last point in that cycle, you can then automatically regenerate distributions over time. And that's what the analytic pipelines are for.
So is this a fair recap? So you look at susceptibility for a specific organism and drug over time in a well-defined population. And if it's drifting, you have to ask, is my panel changing or are my organisms changing?
That's a fair description. Yeah, I would say that's the case. Determining that, I don't think anyone has established methods yet for that last question, but I think you need to at least know what the question is first before you can investigate.
Nice. Thank you. So another potential use of the data that you discuss is checking the accuracy of individual AST results, particularly as they relate to unusual or outlier results. So how are those data checked in commercial systems, and what are the drawbacks to those methods that are currently used?
Yeah, it's a great question. To me, again, the concept behind outlier detection is actually very similar to what I just described for continuous verification. So commercial AST systems use expert systems that are basically performing a statistical test comparing the sample's AST profile to a database of profiles. And if it meets some internal criteria for being an outlier, a number of things can happen, but expert systems, the ones I'm familiar with, will coerce the anomalous result into what it thinks it should be the correct phenotypic profile. And I think this is helpful in many settings, but there are drawbacks, as you can imagine. One is that you don't know the database it's drawing from for comparisons, and it's likely that it's not the exact same distribution of phenotypes that you're seeing locally. Two, oftentimes these coercions are occurring behind the scenes and are not being providers are not aware that these are actually occurring. Not all the time, but sometime. And then three, again, the algorithms aren't tuned to local data. So I think there's some drawbacks to this method, but it is nice that it's sort of automated and we can verify if it happened or not at the bench. In terms of how to replicate that, I think the simplest and most practical would be just to be able to report a z-score for a data point relative to the distribution for that bug-drug combination. So the example I gave in the article is you have a Staph aureus with a vancomycin MIC of 2. It's not crazy, but it isn't that common. And so you could look at the distribution of vanc, Staph aureus, MICs, and then simply say this lies on the tail end of that distribution, and you put a little asterisk on it to either flag it for retesting, which makes sense, or if it passes retesting, the clinicians can say this is an unusual result. Because AST phenotypes are correlated, we can actually borrow information from other antibiotics to see how often these two antibiotic profiles or phenotypic profiles correlate. And therefore, you can build even more robust distributions and statistical tests for seeing how often cefepime and piptazo and ceftriaxone and ceftazidime have a specific SIR combination. I think Reader 2 has that.
Got it, I think.
Well,
so
is it the second part, the correlation of the antibiotics? Is it saying, okay, it's weird to have vancomycin, it's unusual to have a vancomycin MIC of 2 in Staph aureus, but this is even stranger because this is susceptible to clindamycin, for example.
Exactly. Yeah, you're having like a vancomycin MIC of 2, but susceptibility to every other drug. Like that's extreme outlier versus just looking at the MIC of 2 by itself.
Got it. Alex, can you just explain everything to me?
Regular listeners will know that Kelly is not enamored of AST.
It's great. It's really interesting.
Is it growing on you?
But it takes a while for me to wrap my head around some of these AST concepts. But kind of along those lines still, so how could analysis of the existing data be improved on in commercial systems?
Yeah. So, I'm heading outside of the traditional purview of the microlab now into things that I think could be possible with existing data. And I think one of the things as a clinician myself and most clinicians care about is not necessarily how often is this test positive. I'm sorry, how often do patients with the disease have a test positive, but how often is a test positive in patients who have a disease? So that's positive predictive value and negative predictive value rather than sensitivity and specificity. But to do that, you need more data than what is currently given in our commercial AST systems. You need to be able to sum over the population to get a prevalence of your phenotype to then actually be able to say what is the positive and negative predictive value. As you know, they're very dependent on the prevalence of whatever it is you're looking at. So I get an example of how this can be challenging, but I think in general, most labs don't do this, and I think it is probably within reach to do, but it does require a little bit of infrastructure for folks to have built that into their IT systems to aggregate observations over various testing platforms and methods. I've also totally glossed over the fact that when I do these analyses, I have internal algorithms for dropping duplicates, grouping specimens over time together. Like all of that is already, it's very, very important to account for those things because otherwise you're going to be very biased for the patient that has 25 Staph aureus bloodstream, 25 days of Staph aureus in their bloodstream. So I've sort of dealt with that on the back end. The other thing I haven't mentioned is CLSI breakpoints change over time. And so I don't know if you can see I have a bald spot on my head, but I created a spreadsheet of every bug drug combination in the CLSI breakpoint since 2015 to 2023. And it took me a very,
Wow.
very long time, but it's now, I think, up to 12,000 rows. And so what I do is I basically apply the latest breakpoints to an MIC rather than referring to the phenotypic profile back in 2017, because it may be for a quinolone or peptazo be different than it is now. I think that is all part of the back end work that has to go in for you to reliably use these types of analyses.
Let's see if you get emails asking for that database.
I think Romney will kill me if I release that. But she, by the way, was the one who commissioned this review, and I sympathize with you, Ellie, because I'm super, super late in publishing it.
All right. If the applications we've discussed so far are not ambitious enough, let's go on to one that's even more ambitious. So, and they would draw on data beyond those generated by the laboratory. So I'll set the table by discussing. Let's set the table by discussing the many factors that can determine whether treatment of an infection with an antimicrobial is effective or not. So walk us through those, and then we'll get into the data analysis.
Yeah, I mean, it gets to the core sort of task or our responsibility, right? Which is what we really care about is whether the AST results reported by the lab are actually helping clinicians achieve positive clinical outcomes. Right? That's what we care about. But defining a positive clinical outcome is extremely challenging. Determining whether something is successful is challenging. From an ID perspective, we all talk about the host pathogen environment triad. And so even if something is susceptible, there may be host factors or underlying comorbidities or the net state of immune competence that may affect whether that drug works. It still may be susceptible, and there may be something about the pathogen, including its inoculum, whether it's resistant, whether it has persistence, whether it has antibiotic tolerance, and of course, its complement of virulence factors that may confound the relationship between the antimicrobial and the pathogen and affecting a cure. And then, of course, the anti-infective itself needs to be able to penetrate the source of infection, have activity against the etiologic agent. And I would say most important, maybe the clinician's understanding of all of these different factors to be able to properly use the data that comes from the microlab and effect a cure while also not generating antimicrobial resistance at the population level. It's pretty complex.
It is. And given that complexity of all those factors that determine whether treatment of an infection with a specific antimicrobial is successful, what are the challenges to analyzing these data, and what would you take as the best approach?
Yeah, I'm not going to lie. It's really challenging, and I try to apply a pretty critical eye to anything that I do and what other people do with observational data. Um, So aside from the quality of the data itself, which I mentioned some of the challenges associated with that, the analytics used to draw these inferences about whether an AST result will help affect a cure are prone to various types of confounding and bias in the data itself. And one of those arises sort of from the fact that patients who perhaps are more sick when they appear in the hospital lead to the selection of more broad antibiotics to treat them because of the risk of undertreatment in a sick patient leading to mortality. But if you're more sick at baseline, then you're more likely to pass at baseline. It doesn't mean the antibiotic chosen is the one responsible for mortality. It's just that you've associated two things together. And that's what's called confounding by indication. Like the indication for meropenem was that the patient was sick. The patient eventually passed away. It may give meropenem the paradoxical appearance of being associated with mortality. And so there are ways now to control for that. And what I'm describing is essentially a causal inference problem. What is the impact of treatment X on outcome Y given a set of variables, of which one of them is the AST result? And in the past decade, I would say there have been major advances in the field of machine learning for causal inference that have emerged through this really synergy between computational capacity exponentially increasing, increasingly rich data from the EHR itself, breakthroughs in model optimization that make it possible to train very, very complex models quickly, improvements in study design that have come out from research institutions, and the ability to control for confounders. I think all those put together has made this space, ML for causal inference with observational data, a very exciting area of research. And that's not to take away anything from randomized controlled trials. I still think they're the highest level of evidence for the foreseeable future, but they themselves have a set of limitations which are well described. And I think this method that I'm talking about is really more in the space of hypothesis generation. So the example is the Marino trial, sort of the classic example of how our sort of underlying knowledge of the relationship between piperacillin tazobactam, carbapenems, and Enterobacterales bloodstream infection changed. That trial really changed the way people thought. But if you look deeper into the data, it was a more complicated picture. And I imagine a system where if we had the data streams present to simply query our database and say, what is the difference in, say, 30-day mortality between piperacillin and carbapenem and Enterobacterales stratified by MIC? Like, we can do that. Like, we can ask that question and get an answer in a day or two. We would have seen a signal, and then we could have said, oh, this now needs further follow-up through a trial or through some sort of quasi-experimental design. That's the argument that I'm making. Are we there yet? No, but this is where I can see the future going. The idea of being a causal inference engine where the user doesn't have to be technically trained, but can ask a question to this engine in a natural language, because there's a now ability to parse natural language. The engine will create the study, answer it, and then return results back to the user in an automated fashion. That's what constitutes what I think is a learning health system, which is the idea that we can improve the decisions we make for our patients with the data that accrues from routine clinical care. It's not a new concept. It's been around, since 2010 or 9, and but we didn't really have the informatics or analytic tools to be able to do that. And now at least we can begin to consider doing such things. But it won't be easy, to put it lightly. It won't be easy, but in theory, it's possible, and it's good to have that sort of as your goal as we work there over time.
Ray, can you mark a cut at 34 minutes and 5 seconds? Sanjat, that was perfect. You answered the next question also, and I couldn't get the chat to work. No, it's fine. So let's skip question 10. Ellie, if you want to jump right to question 11.
Yep. Right. So Sanjat, this has been really informative, particularly for me. And it's been a really interesting discussion. I have to say, I really appreciated the figures in the paper. So I just kind of refer our listeners to go through those figures. Really helpful to summarize what you've talked about. So, of all of the things that you've discussed today and in the manuscript, what do you think is really near-term accomplishable in like the next, I don't know, 5 years or so? And what are some of the more versus the more long-term applications for this?
Yeah, it's a great question. I would say in the near term, um, the most sort of low hanging fruit to me is to be able to build a dynamic antibiogram,
Mm,
to build the systems to allow the microlab and other end users to quickly say, what is the prevalence of resistance in the previous 90 days on this floor at the push of an app?
mm,
That should be doable. You can say stratify by urine and should spit out a response saying we don't have 30 isolates of urine on this floor, you know? And I think that is not at all a machine learning thing. It's simply a data analytics. It's like a Tableau, like a software could do that, but it doesn't do that right now. It
mm,
could and should, in my opinion, but it doesn't. And that I think requires a fair bit of investment from your informatics teams at your healthcare systems. I will say again, I think our informatics teams are fantastic, but they're not clinicians. And so they don't know what to build unless a clinician comes to them with a project that is solving a problem they think is important. And so it requires very, very tight collaboration between microlab leadership, informatics, and many other people, which I'm happy to talk about. But in the short term, I think it's simply descriptive statistics about an antibiogram.
mhm,
So
mhm,
you've talked about the short-term challenges, and we've touched on some of the long-term challenges earlier in our conversation. What needs to happen to move this forward? What needs to happen to make these applications of data analysis reality?
I think there's many aspects to that question. One of the things that I think would be really great in the longer term is for a community of clinical microbiology practitioners to learn some of the basics of data analysis and sort of become facile with using high performance computing clusters to at least generate some inertia towards um, a sort of to advocate for these types of things being built. Because one of the things that I've found is being able to speak the lingo with the informatics folks makes a huge difference in terms of specifying a project, because they usually don't understand what you're trying to say unless you frame it in their words. Like, oh, I have a SQL database. Can you please query these tables with these views and select these fields? And like, if you don't know even how to frame that, then the conversation takes weeks to ask it what should be straightforward to you. So learning some of the basic terminology and basic concepts in data analytics for us is, I think, helpful to begin that, but it's not enough. And the other thing that needs to be happen that needs to happen is close coordination with antimicrobial stewardship teams, with ID clinicians, with ID pharmacy, to sort of build that community together so that the ask comes from multiple different departments. That makes it a lot more compelling to hospital leadership to say, oh, this is going to impact patient care because of X, Y, and Z, coming from multiple different viewpoints. And then we need to allocate some effort for our informatics teams to build this.
mm,
During COVID, there's a lot of impetus for this, right? For dashboards and
Mhm.
for volumes and things like that. And I think that was
mhm,
helpful. We should continue that process. And to own it, you kind of need to know a little bit about it and work together with people. I do think that ultimately, though, the hospital C-suite has to sign off on this. And so you need to have someone who has the ear of people, 5 levels above you, to say that, oh, the children's micro lab is really doing some innovative work around, personalized medicine, which is a buzzword that I like to use to try to get money. Um, and they're providing individualized antibiograms, but they're showing it can be done, but needs to be now generalized across the hospital.
mm,
And this would impact patient care somehow. And I think it requires sort of that level of support all the way from the CMO, CMIO level down to what we do down in the lab to make this happen. And I think the key point is there needs to be sort of a continual evaluation of how well this is working to justify its existence. So this data generated this outbreak detection, or this data generated a change in policy where we don't use this antibiotic for these patients anymore because we showed there was an increase in adverse events or something like that. Or we stopped using this card because the manual re-verification failed with this new set of isolates, and that actually had the potential to avert this many events. So that's how I kind of think about it. You have to always sell it, no matter what, the bottom line.
I think this would make a great pre-meeting workshop at Microbe, and you should think about proposing it for next year. I would go to that.
Absolutely.
I think it sounds terrific. Well, Sanjat, thank you. This has been such an interesting conversation. I really appreciate you joining us.
I'm honored to be here. I mean, you guys are amazing, and I think what JCM does is amazing. This is a fantastic opportunity. I just a little side note is that Romney asked me to write this review in response to a offhand comment I made in the ASM webinar about in vitro verification that an astute listener heard and was like, what the heck is he talking about? And now it led to a 3,500 word single author review that went off the rails.
So I guess either be cautious or be aggressive, depending on whether you don't want or want to write many reviews, because you may get asked, you may get tapped.
My mouth shut. Yeah, no, it was actually a fantastic thought exercise for me to be much more thorough and logical about the rationale behind.
That's great. That's great. Ellie, if I'm not mistaken, our next episode will be recorded in front of the live audience at Microbe.
It will, and it'll be great. We're going to have some audience interactions.
Good.
We're going to have some exciting guests.
Do you want me to do limericks again?
And we're going to do limericks. We can't not do limericks. So it's going to be fun.
Good. Well, that gives everyone something to look forward to. Thank you both, and thank you to our listeners.
Thank you very much.